8. You're working in the store in the summer, you lift the bag of fertilizer with this force, and they want to know what's the mass of it and what's the weight of it. All right? And it accelerates upwards at this. So, let's start. We'll do number 8. And I'm going to start by doing my force diagram, which is my Y, no writing needed. So, here's my bag of stuff. It's going to have its weight down. It's near the earth. I'm applying a force upwards on it. And it is accelerating upwards also, it tells me. So there is my force diagram. That is what yours would need to look like, or at least have those forces on it and that acceleration for full credit. So look at yours. If you are fancier and drew the nice picture of the bag and everything, that's great. But the credit comes from, do you have the weight on it? Does it point down? Do you have the force on it? Does it point up? Do you have the acceleration label? Does it point up? You know, this is where the credit for this comes from. And that is your only requirement for the Y, is that diagram. All right? So now I'm going to use that diagram to help me organize the problem, because I only have my one equation. I'm going to actually start a little bit early here. I only have my one equation, which is the sum of the forces, adding up all the forces, is the inertia times the acceleration. It's my only equation for this whole section. Everything else is an identity. You know, like we're going to have to use, what is weight? Well, weight is the mass times the gravitational field strength. That's an identity. That's saying that's what weight is. It's not an equation. Which direction are all my forces and accelerations in? The Y direction. So I don't have to worry about the X, so I'm just going to say just the Y there. And now I use that diagram to organize it. Which way do you guys want to call positive? Up. Okay. So I've got positive F, right? Plus, that's what the sum means. Add them all together. Plus a negative F sub G, because it's pointing downwards, equals my inertia, M, times my positive acceleration. You could put your numbers in at any point. I'm going to keep my numbers out for a minute. If you want to see it worked with numbers from this point, look at C Block's video. So I'm going to try to do this one a little differently I'm going to appeal to different types of learners, okay? So good, I've got my setup now. If I look at my equation sheet, let's see, I have the honors one up, but I notice I have the identity that the force, the weight, which is the force due to gravity, is the inert mass times gravitational field, mg. So I'm going to replace that in here. Okay, if I drop my extra signs here. Okay, so I have F minus, rather than FG, I just looked up that I can replace that. mg, so minus mg equals ma. Yes? Does everyone see what I did there mathematically? Okay. I want to know m, so I want to get them together. So I want to get m by itself as much as I can. So I'm going to bring the m's over to the same side. Because now, really, in essence, most of the physics is done. Now I just have to do that pesky math stuff. All right? So algebraically, I'm going to rearrange it so it's F equals ma plus mg. That okay? Yeah. And then my next algebra step would be F equals m times a plus g. And now F over A plus G equals M. Let me know if any of that algebra I went too fast or you need me to explain how I did what I did. Good? Okay. So now I'm going to put in my numbers. They tell me my force, 116 newtons. 116 newtons. My acceleration, 0.751. 751 meters per second squared. I'm on Earth, so I know that my G, and also from my equation sheet, is 9.80 newtons per kilogram. All that equals M. Meters per second squared and newtons per kilogram are the same units. They come out the exact same. All right. You can tell one way you can tell that is if you go to the equation sheet here, and you go all the way down the bottom of the back page. You have G equals 9.80 meters per second squared. That's an acceleration. It also equals 9.80 newtons per kilogram. So if you're looking at it going, oh, I can't add meters per second squared and newtons per kilogram, realize that you can. Maybe it's one of those things to put in your memory banks. So now I just do my math. Let's see. 116 to 116 divided by parentheses 0.752. Right? 751. 1 plus 9.8 parentheses, enter. I get 10.994, which if I round that to 3 sig figs is going to give me 11.0. How do I? Well, you never really asked the question, so don't consider it stupid. You figured it out. That's great then. So my answer for M is 11.0 kilograms. But then they also asked me what's the weight. And I know from my equation sheet that the weight is the mass times G. So F sub G is my, and here I should use my 10.99, whatever it is. 10.9942 kilograms. That would be times 9.80 newtons per kilogram, giving me an answer in newtons. So this times, let me do my math first. 108. So I get 108 newtons. So let's see if those are right. Let's try. Let's see. All right, I'm going to start on number 9. I'm not going to do A and B. Of course, A, tests whether or not you understand what Newton's third law is, and B, whether or not you understand what Newton's first law is. So they're good on that. So I'm going to go on to number 9, part C, where it asks about Tom's acceleration. And so for this one, I actually need 2 separate force diagrams. I'm going to do them right next to each other, though. So this is number 9. And we'll have, here's Tom. And here is Tom's sister. There, of course, is going to be the weight on Tom's sister. There'll be a normal force on Tom's sister. And then there's a force, and it's on the sister due to Tom. So we label it as force ST. Force on sister due to Tom. And then on Tom, course, he's going to have his weight and his normal force. And then there'll be a force on Tom due to his sister. And from Newton's third law, we know that those are the same magnitude, they're just in opposite directions. Yeah. Sure. So we know from Newton's third law that the force on Tom's sister is just as big as the force on the sister due to Tom. Right? So this actually, probably if I was to draw a line, this would start my how part of this. And, oops, well, you almost let me forgot. Tom would be accelerating this direction, and let's call it mt for his mass. And then the sister also has a mass, ms, and is accelerating this way. So that would be your full force diagram needed for full credit on that. Some of you might want to look at that just to compare to what you had. All right? But that has all the necessary forces. S for sister. Everything in green has to do with the sister. Everything in black has to do with Tom. S. All right. So now they want to know the acceleration of Tom. We know the individual masses. We know the acceleration of the sister. So I'm just going to look at this horizontally because vertically, while it's interesting, it doesn't tell me anything about the acceleration vertically. So I'm going to see if I can do it without doing the vertical parts just to make my life easier. So, and I'm going to I'm going to do them in parallel here. So for the sister, some of the forces in the x equals m ax. This is for the sister. There's only one force on the sister, FST. And then you have the inertia of the sister and the acceleration of the sister. Coming over here to Tom, where you really have a very, very similar situation. Some of the forces in the x is max. The only force on him is force on Tom due to his sister. And we have the inertia of Tom and the acceleration of Tom. And this is where knowing Newton's third law helps me. Notice that the force on Tom due to his sister, the force on the sister due to Tom are the same, right? So I can bring these two things together and say that the mass of Tom times the acceleration of Tom equals mass of the sister times the acceleration of the sister. And I'm interested in the acceleration of Tom, so I'm going to rearrange this to have acceleration of Tom by itself. So the acceleration of Tom is the mass of his sister, the acceleration of his sister, over the mass of Tom. See, they tell me his sister, I believe, is 15 kilograms. My acceleration for this one, 2.5. Tom's is 58, so tell me she's accelerating at 2.5 meters per second squared, and my Tom is 58 kilograms. And now I can do my math. Well, I can do my numerical calculation. I've already done math. I read it from my problem where it said the sister accelerates at, I think it's the wording they use, right above where you put in the answer. Yeah. So, let's see. Parentheses. 15 times 2.5 close parentheses, divided by 58. And then I get 0.64655. That makes sense. He's about 4 times bigger than her, more inertia than her, going to accelerate at a quarter of what she does. Seems to make sense. So that would round to 0.647. Meters per second squared. So let's give that a try. So we're going to do number 7. Grocery bagger pushes a 5.5 kilogram bag of potatoes this way. The net external force. When you read net external force, one thing to keep in mind is say, oh, that's the one that causes the acceleration. So whatever direction I put that net external force, that's the direction it's going to accelerate also. And so I have a lot of freedom of how I arrange this one. I'm going to arrange it to make my life easy. So this is number 7. I'm going to say I've got a surface here, and I have my bag of potatoes. Going to have a weight down, of course. It'll have a normal force up. I'm going to say that I'm pulling on it or pushing on it with a force F, and therefore it's accelerating in that same direction. When you hear net external force or net force, it means it's not the only force on it, but it's what they all add up to. So what's going to happen with the normal force and the weight here? They're going to, in essence, cancel each other out or equal each other out. So I'm only going to worry about the x direction here again. And in the x direction, I have, I'm going to start right up here. Sum of the forces in the x, MAX. It's kind of nice only having one equation. You always know what physics equation to write down. I have one force, F, the inertia of the bag, and I have one acceleration, A. Let's see what I know. What do they tell me? What do they want to know? They tell me the inertia. They tell me the force, and they want the acceleration. So I'm going to rearrange this for the acceleration and have F over M equals A. They tell me this is 60 newtons. Mine was 5.5 kilograms. And that's going to equal A. So 60 divided by 5.5. I get 10.9090909. So 10.9 meters per second squared.